Okay. So, I'll do a quick review of what we did last time. Um, okay, so if you guys weren't here for last class, I think we worked with equations and you guys will mainly need to know how to use the equations that I've given. And I'll give you guys the equations that we did last time as well. You just got to so if you don't understand the equations, don't worry about it because I didn't explain how we got those because that's a little more complicated. But oh, Lucas is here. Perfect. Okay. So Lucas is the other tutor. I know he hasn't been here for the other classes, but he'll be in charge of um this this class with me today. It'll be a lot easier now because I can answer questions in chat or Lucas can answer questions in chat whenever you guys have questions. But say hi, Lucas.
Hi guys.
uh, and then are you on your computer?
Yeah, yeah.
Okay, I have my iPad on the side to help annotate, but um
So should I screen share the slides or okay.
do you actually do you want to screen share? I think it'll be
Sure.
better if you screen share, yeah.
And so we're starting with.
I was gonna review like the equations a bit, like the potential and kinetic energy equation, and then the power equations as well, just because I
Okay,
know some
okay.
people weren't here. So go back a few slides. Back, back, back. Actually, no, you can start at power. Just start at power.
Okay.
After
Yeah.
this. Yeah, yeah, right here.
Okay.
S-
So
you got it? Yeah. Go ahead.
yeah, so power is just the rate at which work is done or energy is transformed. So it's like work is like you applying a force over a distance and power is like at what rate you do that. So like you would do this many joules per second, which is like a watt, which is the user unit of power. Um So yeah, it follows the same kilo, mega as like what we use and everything else. Horsepower is 746 watts. You might have heard of horsepower in like engines and stuff, and that's just another unit of power. I don't know if horsepower is actually like accurate to like one horse's power. I'm not sure. But
Okay.
yeah, that's what power is. Okay, so power is work divided by time. Yeah,
And then,
because
yeah.
it's the unit would be like your unit of work per like your unit of time, which makes sense because we know the formula is work divided by time. Yeah.
And then just to cover what like work exactly is again, work is just the change in energy basically. So if we, I know this will be used for the hard question, but we covered two types of energy, kinetic energy and potential energy, correct? And
Yes.
basically what work says is kinetic energy, the second kinetic energy plus the second potential energy is sorry, this minus, yeah, sorry, minus the kinetic energy of the first plus potential energy of the first is just equal to the change in energy. That's right, right, Lucas?
Yeah.
And then for the people who weren't here for the kinetic energy and potential energy, it's just 1/2 mv squared is equal to the kinetic energy, and then mg H is equal to the potential energy, and M is equal to the mass, V is equal to velocity, and then same thing here, M is equal to mass. G is equal to the gravitational acceleration, and in this class, we're just gonna say that G is equal to 10 meters per second squared because 10 is a nice round number. It's actually equal to 9.81, but I don't want to make it too complicated. And then H is a height. And notice how, like, in potential energy, if we're using, sorry, notice in potential energy, we use height, and then in kinetic energy, we use velocity. Like you won't ever use height with kinetic energy, or you'll never use velocity with potential energy. And this is just a quick review of everything. If you guys have any questions, feel free to ask in chat. I can answer while Lucas teaches.
Yeah, that was a good explanation. So after this, yeah, the connection between energy and power. So like I said, power measures how quickly energy is transformed. So like rearranging the formula, energy is equal to power times time. Yeah. Wait, can I re-see that? Um,
Oh, the equations, yeah.
you want to rewrite the equations here? Okay, go back to the slide.
Actually, I'll make it a lot neater here. I'll just keep it up on this corner for you. You can.
Oh yeah, okay. So if you like, you see kilowatt hours like a lot in the real world, and that's just like a measure of energy because it's kilowatts is like 1,000 watts, and hours is obviously a measure of time. So kilowatt, you can think of it as like kilowatts times hours, and that's just equal to energy here. So yeah, example here, a 2 kilowatt heater used for 3 hours. The amount of total energy used, because we know we're given uh the rate of power and also the time to find energy. The formula's up here. Energy is just equal to power times time. So it'd just be 2 times 3 equals 6 kilowatt hours. Pretty simple. Has everyone got it? Okay, I'll move on. Some practice problems. So this should be some, you guys want to do these in chat and then we go over them after.
Yeah, I think we also did this last time. So let's just go over or like you guys can just do problem three. Just do quickly problem three, and then Lucas will go over the answer.
Okay, okay.
Watch some video.
You got it, Lucas?
Um, I haven't gotten any answers yet. Are they supposed to be messages to
Oh.
me? Have you gotten any?
Um. Oh yeah. Okay. By the way, there's two of my um. I have two devices connected. Could you guys? I'll rename this one actually.
Name it like iPad or something. Like the
Yeah, I'm just gonna rename it iPad so you guys don't private message to the wrong one. So if you guys private message to my other one, that's okay for right now because I can see it. But just make sure to message it here. Okay. Yeah, I think you can go over the answer. There's a couple people having
okay.
trouble, I think.
Okay, I'll go over the answers now. So
Yeah,
let me go
go
back
over
to
it slowly.
okay. So I'll draw a picture. Drawing pictures is like really oh, I don't like this color.
Okay, okay.
Here.
Um,
So we have a oops, say this is really hard to draw with.
sorry.
We have a
Did you remove
10.
annotation?
I can annotate. I don't know if anyone else can.
Wait, I can't annotate.
Oh, Oh wait, my screen's paused. Never mind. That's why. Here.
Oh, there we go. Okay, okay.
Okay. So 10,
Yeah.
do you want to draw it?
Yeah, yeah.
Okay.
10 kilograms. What? Should I just say this is a distance of 2 meters and then I'm gonna use 10 meters per second. 10 meters per second squared, sorry. Right.
Yeah.
Equals H. M is equal to 10 and G is equal to 10.
Yeah. Okay. So if you guys remember, work done is force times distance, and if we're lifting a 10 kilogram box up 2 meters, like the force we're applying to is just to combat gravity. And like we can assume this at like a constant velocity. So gravity is pulling down on this box with a force of uh whatever the weight is. No, the mass is times the gravitational acceleration. So that would just be 100 here, right? 100 newtons. If we're assuming g is equal to 10, right? It's a downward force of 100 newtons. This is right, right?
Yeah, that's you're basically just using potential energy. I think you should use a potential energy formula, no?
Oh,
Because that we
changing.
have because it's we you're basically doing that, but just like because I had the because potential energy is equal to joules as well. So you could either way is fine, but I taught them
Also,
using potential energy. Do you want me to
okay.
explain this one?
Wait, yeah, you can do it then.
Okay, okay. Um, so what Lucas was doing was like the other way where we use force times distance, but I think the way I would go about this, especially because I have like the potential energy formula up here, is we're given the mass, which is 10 kilograms, and then the we're given gravitational, which is we're given G, which is also 10 in this case, 9.8 or 10, it doesn't matter, times the H, which is two meters, right? So when we multiply this, it equals 200, correct? Because we can also use power, or we also use the power equation. So we need to find the energy, which is what I'm doing right now, right? The energy is equal to h is the height. So my first sorry, I should put this in goals, right? So first we identified that power is equal to energy times time, right? And we know that the time is 2 seconds. So the time is not the problem. We just need to figure out what the energy is equal to, right? Where did the height come from?
It was
The
given to
height,
us.
yeah, the height's given right. It says you lift a 10 kilogram box 2 meters in Sorry, I should probably say you lift a 10 kilogram box 2 meters high, just to clarify. But it says whenever you see 2m, you're just gonna assume it's 2 meters. So this is just equal to 2 meters high. So, like I was saying, the first goal is to figure out which equation to use. And we know we have to use a power equation, right? Because it's asking for the power output. Once you figure out that we're using the power output or what we're figuring out the power output, now we know that it uses energy over time. And since we already know it's in 2 seconds, we place the two here and then you get energy is and then you have to figure out the energy, right? That's the main difficulty that we face in this equation. So we try to gather as many variables as possible that we are given, right? So we have the mass, we have gravity, and then we have how far it's lifted, right? And since we can relate that to this, the potential energy which is also equal to energy, because energy is in the name of potential energy, we can kind of use that to figure out that we just put mgh up here, right? And when we do that, we can solve for mgh because now we can just substitute all the variables given to us, and then we get 200 over 2, which equals 100 watts. or 98 watts if you use 9.8. Does that make sense to you guys?
Nice. Okay.
With the way Lucas was doing it is like also correct. Lucas, could you go back? Wait, does it force times distance is equal to no, energy, right?
Force times distance is equal to work done.
Yeah, yeah,
Um,
yeah. So technically you could also say like what Lucas was doing was he was putting force times distance up here. And if force times distance, since we know the distance is 2 meters, sorry, D is equal to 2. We just need to figure out the force, which is mass times acceleration. And acceleration is just 10 because the gravitational acceleration is just 10 meters per second times the mass, which is 10. He just did it this way. Both are correct. I just thought we used the potential energy because that's what I like you guys are more familiar with. But
yeah,
either way is fine.
they both work fine.
Yeah.
That
Do you want to
should
Do you want
go
to go
on.
to the first problem as well? Just like
Okay,
because
okay,
to get these to get the kids more familiar, like refresh their brain.
okay. So this one's like
Um,
a little bit more simple, I think. Should we
yeah,
wait for them to do it?
yeah. Give them a second. This one's like a lot more simpler in my opinion than the third problem. So go ahead and do the first problem.
Okay, we'll give you like a minute to do it.
Oh, sorry. Did I? I want to keep my other. Lucas, could you go back to the screen for a second? Oh yeah, thank
Okay.
you. Hmm.
Yeah, sure. Do you want to put the formulas back up?
Yeah, wait. That's what I was trying to do, but oh, there we go. Okay, now I see it. P E. And then these units that I put up, they're like just for this case. Like energy could also equal kilojoules or like whatever. Like I'm just saying like in this case, energy, we're just saying energy is equal to joules, right? Don't like don't take this as a given for every single equation or every single problem you see, right? It's just in this case. Sorry, I'll go through
Oh,
all the responses now. Sorry. Oh, are you guys oh, some people are doing oh, okay, but some people are just doing both problems. Yeah, if you guys are done with the first one, try to do the second one. Um, Go ahead and do Lucas, you can start the first one.
yeah. Okay, so we know joules is equal to energy, right? So we know joules is a unit of energy here, and we have 6 seconds, which is a unit of time. It's asking us for power, which is really convenient because we have this formula right here, right? Power is equal to energy divided by time. And guess what? We have energy here and we have time here. So it's just a simple division question. 1200 over 6 power output is equal to 200 watts. Everyone get that? Does that make sense?
And then you can just go over the second one as well then.
Okay. So in the second one here, we have watts, which is the unit of power here. And then we have time. And then we have how much energy does it use? Questions asking for energy. So we're looking for energy here. We're going to be using this equation again. We changed my pen color here. So we know
Yeah.
we can rearrange this equation here. P, which stands for power, energy over time. This is equivalent to, you guys know if you multiply both sides of the equation by like the same thing, it's this like you can do it, it'll stay equal. So we can turn it into PT by multiplying both sides by time. It's equal to energy. And guess what? We have power here, our value of power here, and our time value here. Um, Something we should do. I'm pretty sure joules is in seconds. So we have to change this
In this
2
case, yeah.
minutes into 120 seconds to get like the correct unit formatting. Because like if we plugged in two for time here, it would be incorrect because it's actually 120 seconds and energy in joules is looking for seconds. So yeah. What is this? Yeah. So it's just 120 times 1500, which is I don't know what that is actually. I don't know that off the top of my head. Calculator here.
Hmm?
I'm using my calculator. This
I think
is
it's 180,000.
180,000, yeah.
Yeah.
180,000 joules. Everyone got that?
Or you could also
There's
just
an
say
extra zero here.
180 kilojoules.
Yeah. Nice. We got it.
Yeah. So just the key for the second one was to convert the 2 minutes into seconds. I think that
Yeah.
was the hardest part about that because some people mix up using minutes with the watts. But if you're gonna use, I don't think you use watts. I think it's watt hours or for yeah. So if even if you didn't want to use the seconds format, you would have to do 2 minutes and then you have to do 2 minutes and then you have to say like if you wanted to put it in hour format, you would have to or divide this by 60 because there's 60 minutes in an hour. So then you would have to do 1/30 and then you would have to do that conversion. That's a bit trickier, but um we're just gonna stick with the seconds here. So make sure to just convert into seconds before you do that. But yeah.
Nice.
Do you guys
Okay.
have any questions about this? Any of these problems? I think this is a good refresher on what we did last class.
Yeah, I think after this we have like a more difficult question. Okay, yeah.
Yeah, we didn't cover the difficult question last time.
Here.
We'll
Up there.
we'll give you guys 4 or 5 minutes for the difficult question.
You guys can read it here.
I'll put the equations back up.
Yeah. Okay, we'll give you 5 minutes to do this question. We'll come back at like 2:35-ish.
Yeah. And if you guys, I'm just gonna do delta because so the triangle you see on the screen, if you guys weren't here for that class, the triangle just means the change in energy. So which is just work, right?
Wait, I would try drawing a picture for this question because, oops, that's actually pretty hard without being able to draw a picture. I'll try drawing like one.
Um, we were gonna give you guys until 2:35, but if you guys still haven't solved it until then we can give you guys extra minutes. Okay, I'll draw a picture for you guys. Wait, it's actually hard if you don't. Lucas, do you want to draw a picture then? I can try to do the other because your screen gets paused.
Okay. Oh wait, yeah, I can draw it here.
There has to be a better way. Okay, I'll find it then.
So okay.
Do you guys need more time? Do you guys think you guys will be able to do it or? Okay, sometime. A little. Okay, yeah. We'll give you guys until 37 then. Lucas, as you can tell, Lucas's drawing skills are quite
Yeah, I'm just draw a
the
three body
artist.
diagram.
Oh, that you might. Yeah, they don't know what a FBD is, but
Oh, they can learn now.
yeah, they'll learn. But do you need to use FBD for this?
It might help to visualize. Actually, I'm not sure. You don't even have to know.
It might have to. It might help with visualization, but does it help?
No, it doesn't because you don't have to use forces to solve this question.
Yeah, that's what I was thinking.
Better, I'll draw.
Just draw a normal picture, I think. Huh, okay. Hmm. Okay, I like this one. Star. I think I think if you guys
You guys
I
want me
think
to go to
Lucas
the
can go
answers
ahead.
now?
Yeah, I
Okay.
think Lucas. If you guys weren't able to solve it yet, that's okay.
Oh, these are
What?
supposed to be like speed marks under the elevator. I guess it's kind of a bad drawing, but like like they draw like lines to show like it's moving. Okay, whatever. They're supposed to be like marks, whatever.
Oh my
So,
Lord.
okay. Well, I can just delete this. Is there like a move tool? Okay, that's not what I wanted to do.
Okay. But so basically what Lucas is going to start off with doing is he's gonna list the equation that will find out how much power he needs, right?
Yeah, okay, so to do that, we have to like first look at the question and read it all. So let's try to understand what it's asking for. Whenever I'm doing a physics question, I like to underline like my units and like the numbers they give us in the question. It's super helpful to know like what values they give us. So a 1500 kilogram elevator, this is mass, starts from rest and reaches 4.0 meters per second. This is speed or like velocity in 5 seconds time while moving upward, rising 10 meters, which is a distance. During that interval, the Kibble tension does work that increases both gravitational potential energy, which is given by mgh, and kinetic energy. What is the average power output of the system described? So average power output, what it's asking for is pretty much just power because over the total energy change over time. So yeah, we're using this equation right here. Um, define the change in energy. First, we define the work, okay, so change in energy is just work. So to find the change in energy, we have to find the work done by the tension of the rope and by the change, I think,
If you ever find
the
this hard
change,
to write
the
on your
change in
screen, and
gravitation. Yeah.
yeah, I just tell
Uh,
me if it's hard to write for you, because then
okay,
I can
okay.
just go ahead.
We gotta change the change in gravitational potential energy and kinetic energy. Yeah, that's right. Okay, yeah. So, change in gravitational energy. Starting at the bottom, we can set this as equal to 0 here. Like h is equal to like the height of 0. And we know it's brought up to a height of 10 meters. So we can call this, I don't know how to draw this. But anyway, like imagine bringing it up to a height of 10 meters. So that means we started at potential energy of 0. And this is changing over to mass, which is gravity times our new height here, which is equal to 10 meters. So it would be 1500 times 10 times 10. That is our change in potential energy. Uh,
And the
yeah,
same thing for
change in
kinetic
potential energy.
energy. It goes from
Actually,
velocity of zero. It goes from velocity of 0 meters per second to velocity of 4 meters per second. So just the same exact thing that Lucas did with um the height, but except with the velocity for kinetic energy. So it'll just
and
go
this,
from what's that? Okay, 1500 kg times what? Five? No, sorry, four. Four squared. And then I'll write this a bit neater since I know Lucas is on computer.
yeah, it's kind of hard to write. So anyway, change in potential energy is 147,000 joules. You can think of this as like when you're lifting an object up from off the ground, you're giving it potential energy because like it has the potential to drop now. So like when we raise the elevator from 0 meters to 10 meters and it's 1500 kilograms, we're bringing it from zero potential energy to 147,000 joules of potential energy. We also need to consider the change in kinetic energy because this elevator is accelerating. So there's also kinetic energy given as like the rope is pulling it up.
Hmm.
Um, it's equal to whatever this value is here. So it's 0.5 times 1500 because we know that kinetic energy formula is up here, 1/2 mv squared. So 1/2 times 1500 kilograms, which is the mass times 16 or the velocity squared. It's 12,000 joules.
Do you say 12,000?
12,000 joules, yeah.
Okay.
So now we have two
Two.
values for the change in energy, like over this
Oh, do you use
four,
9.8?
yeah, I use 9.8.
Okay.
It's 12,000 joules of kinetic energy change and 147,000 joules of potential energy change.
I'm just gonna
And now we
keep it.
know the change in energy over this 5-second period. And we know power is just a change in energy over time. So we can do 12,000 joules plus 147,000 joules divided by 5 seconds to give us our average power output. Do you want me to write it? I got it. What is J? J stands
Joules.
for joules. It's just like a unit. It's like the same as like kilograms for mass. It's the unit for energy or work, since work is just change in energy. Yeah, I actually got it.
Yeah, we were just yeah, it's the same, but um I think the way Lucas did it was really nice. He went through the question. I like how he underlined what he thought was important. That was really nice. And then he underlined, you notice he underlined the actual question I was asking. Um I know it's kind of silly, but there's like times where I like solve for like things that are completely unnecessary that I need to solve for. Like
Yeah,
and like just focusing on the actual question just makes it a lot easier. So if I know that it's asking for power, I can instantly think, oh, what's the power equation? Okay, change in energy over time. And then I can go for that from there. Oh, I only need to know energy and time. Since I already know the time is the bottom, how do I solve for the total energy? The total energy is equal to the potential energy plus kinetic energy. And then you would realize, oh, it's this is great because I'm given all the variables needed to solve for any of the or for both of these things, right? And then once you know that, it just becomes a lot easier to do, right? Whatever 162,000 divided by, let's do that actually. 162,000 divided by 5, 32,400. So if you got around 32,000, that's correct. Because I know some of you guys use 9.8, some of you guys use 10. And does that make sense to you guys? Do you guys have any questions? I'm just responding to some people in chat because I know some people had questions. That's a quote. Oh my God. I'm gonna have to quote you on that, Lucas.
there's like
Science
a
is
real
just
quote.
crude. Is it? Is it?
Yeah, let me find it. It's like any sufficiently advanced
Time.
technology is indistinguishable from magic.
Yeah. Oh yeah, by the way, I don't know if you're here for Bob, but like
Who is
these
Bob, bro?
the kids like I used Bob for an example, like the previous classes, and now they're attached to Bob.
It's okay, but like as like in like a word problem or something. What is
Yeah, yeah,
Bob?
yeah, yeah. Like I was like
Okay,
for
yeah.
especially for like force, I like drew Bob pushing a box and like I made his arms like extra long and they don't think he's human anymore. Because they
It's
also
okay.
think he can fly.
We can bring Bob back. Okay, should we move on from this question?
Yeah. I'll be answering people's questions in chat about this question, but you can move on as a whole.
Okay, let me get rid of the annotations.
Yeah, you got that? You're all
Oh, it's
right.
gone. Okay. So I guess we're starting with mechanical versus non-mechanical forces, probably. Oh no, energy, I guess. Okay. So mechanical energy, are there infinity atoms? No, there are a limited amount of atoms in the universe, I'm pretty sure.
Yeah. just keeps on expanding.
Yeah, but it's like vacuums in between. It's like matter's not increasing. It's like stuff is getting farther apart. Okay. Mechanical energy is the energy an object has because of motion or position. This makes sense, right? Like because if you think about it, mechanical stuff is like physical stuff. So like mechanical energy is like the energy an object has because of its physical motion or position, right? Yeah, that makes sense. So it includes kinetic energy, energy of motion, like moving stuff has kinetic energy, and potential energy, which is stored energy based on positions. Like bringing something up has the potential to fall, which like will release its potential energy into kinetic energy. That makes sense too. Total mechanical energy is the sum of kinetic energy and potential energy. That's like a definition, I guess. And mechanical energy can be transferred or converted, but is conserved in ideal systems. So what is an ideal system? An ideal system is where, actually, I think an ideal system is defined by total mechanical energy is conserved. There's
Hmm.
there's no energy leaving or entering the system.
We covered that in last class, I'm pretty sure.
Oh,
You
wait, how
guys
did you guys
remember?
define it?
We just like defined mechanical energy as something that doesn't like lose energy to like friction or like heat or
I see.
sound. Yeah.
Okay. Okay, so a moving car has kinetic energy. That makes sense. It has mass, it's moving through space. Kinetic energy is 1/2 mv squared. A stretched bow stores potential energy in like the string, the tension, I guess. Yeah, we can call it that. A roller coaster at the top of a hill has high potential energy because it's up high, and if it goes down, it'll turn into kinetic energy from gravity accelerating it. And a compressed spring holds elastic potential energy. This makes sense because like push a spring together, it's gonna push against you, and if you let go, it's gonna release energy. Non-mechanical energy. So non-mechanical energy is like everything that's not related to motion or position. It's like thermal energy, chemical energy, electrical engine energy, nuclear energy. Can you guys like think of any other examples? I think I'm probably missing some. But yeah, these energies often convert into mechanical energy or vice versa. Do you guys have any examples? I think solar energy counts. Yeah. Light radiating through space. Can we use nuclear energy and mechanical energy to make a new Earth? Maybe. That's um, I
You guys are
think
creative.
we need a lot of like new mass to make a new Earth. I don't know if we can get that mass anywhere. I guess maybe if we went to Mars and like put a bunch of nuclear reactors, we'd
I
have
mean,
energy to like terraform
even
it,
if you did
maybe.
that, even if you do that, you need the right atmosphere. Like,
Hmm.
need like the right air to breathe, the right like there would have to be a lot of things to go
It's
right in
possible though.
order for
Anything's
the
possible with enough time and money. So yeah, we probably could make Mars into Earth with enough time and money.
terra. That's
Okay.
what you call terraforming.
Hmm. Is it possible though? Yeah, I assume it's possible. You can, because remember,
That's what
everything is just
Elon.
made out of elements, and
Hmm.
like our atmosphere is just a specific mixture of elements, and these elements exist everywhere. So like if we just mix them together, we can like recreate it. Okay. Relationship between the two. Energy often changes between mechanical and non-mechanical forms. Something to know is that energy is never destroyed or like created. It's always just changing forms constantly. So an example, a car engine converts chemical energy, fuel, into mechanical energy motion. That makes sense, right? Because like fuel and gasoline, when it ignited it spins. How do car engines work again? They like push pistons, and these pistons like move the wheels, something like that. Friction converts some mechanical energy into thermal energy. So like if you like rub your hands together, you can feel like heat, right? That's because friction's doing that. It's taking this mechanical energy of you like moving your hands together and turning it into thermal energy. Which is why like friction also slows things down because it's taking away kinetic energy and turning it into thermal energy in other forms. Understanding both types helps explain how energy flows in systems. This makes sense. What about getting a burn on carpet? Yeah, that's another example of
A
friction
rug burn.
turning, yeah, rug burn.
That's creative.
They hurt pretty bad. But yeah, it's friction from your hand sliding against a high friction surface, which is like your carpet. There's a lot of tiny hairs there. It'll slow your hand down and turn kinetic energy into heat energy, and it'll burn you. Activities, let's see. Here are some questions. I'll give you some time to answer these. Uh, I think like 5 minutes should be fine, or like 3 minutes. You
And then
guys
if
can
you
do
feel like,
these.
yeah, if you feel like any of these are, um, yeah, actually, yeah, just do all of them.
Oh, working on these questions right now. If you guys have the answers, you can just message me. I got them.
Oh yeah. Also, since me and Lucas are here today, I don't think it would be like if anyone's like stuck on a specific problem, it wouldn't be a bad idea if I like if one of us just took you guys into a breakout room to do the problem. Like if that's ever the case, just tell us and tell us like just request DM one of us if you want to go to a breakout room to solve one problem with us, and we'll be more than happy to because there's two of us. Usually we couldn't do that because a TA wouldn't be able to help, but since both tutors are here today, feel free.
Yeah. Okay, should we start going over these answers?
Yeah.
Okay. So what is the formula for kinetic energy and how does velocity affect it? So kinetic energy is equal to 1/2 mv squared. So, okay, so 1/2 mv squared, m is mass, of v is velocity. How does velocity affect it? Um, since if you notice here, velocity is squared in this equation here. So as like speed goes up by one, like kinetic energy will increase by like an exponential factor. So like speed matters more than mass and kinetic energy. That's how you can think of it. A 3 kilogram object speeds up from 2 meters per second to 6 meters per second. How much work is done on it? So work is just change in energy, right? Change in energy is equal to work. And we know this object starts with some amount of kinetic energy and it speeds up to 6 meters per second, which gives it a new kinetic energy value. I got a question. If the velocity is greater, kinetic energy, oh no, that's an answer. Yeah, that's correct, I guess. So Solving for this, 1/2 times 3, which is the mass, times velocity squared. Initially, it's 2, and 2 squared is equal to 4. And it turns into 1/2 times 3, mass stays the same, times 6 squared, which is the new velocity. So, this is a 6, what's the unit? Joules, right?
Yeah.
Yeah,
Wait, yeah.
6 joules. And this is, just 9 joules, right? No, it's not.
Hmm?
36 or choose 18, 18 times 3. What is 18 times 3? I've done math in so long. 40,
54.
54, 54, 54 joules. So now we have the original kinetic energy and the final kinetic energy. If we subtract this, it gives us the change in kinetic energy, which is equal to work done, and that's just equal to 48 joules. Ta-da! That's our answer for that question. And what is the key difference between conservative and non-conservative forces? This one is like kind of tricky, especially since we went over like, yeah, this one's just kind of tricky. So conservative forces, um, it only depends on the start and end points, not the path. That means it's path independent, which is like the definition of it. Um, non-conservative forces like friction is non-conservative. So like if you take a longer path, friction is going to do more work. So it'll it's not non-conservative. I don't know how to explain this.
Yeah,
It's kind of
you
difficult.
can you can kind of think of it as like conservative forces like keep the energy in a system while like non-conservative forces like take energy out of the system,
Hmm.
right? So if you think of like
Yeah,
a car like rubbing its tires against the road, that causes friction, and friction takes energy out of the system. So friction is a non-conservative force, right? It's,
yeah. That's how you can think of it. That works actually. So what is the law of conservation of energy state? It's kind of in the name. Energy is always conserved. Energy cannot be created or destroyed. So it's like
Mhm.
always just changing between different forms of energy. Like it'll never be destroyed.
And we have a lot of activities, but I don't know if you guys we have like seven. I don't know if you want to go through all these.
We can like
Because
kind of like speed through them. We don't need to
yeah,
like
because
sit here and
we
count
have a
through.
lot to cover, I'm pretty sure.
Yeah. So kinetic energy depends both on mass and speed. Uh, we know the formula for kinetic energy is 1/2 mv squared. Mass and speed are both in that equation. That's true. A stretched rubber band has potential energy. This one is true because remember, if you let back, it has like elastic energy. It'll snap back. That's true. The work energy theorem only applies when there is friction. Work energy theorem. What is that again?
That's false.
Yeah, yeah. This is false. Work energy theorem is net work done on an object is equal to the change in its kinetic energy. This applies like whenever. It's not just when friction. Wait, actually, is what would slow kinetic energy? What would
Hmm?
like take away kinetic energy if it's not friction?
It could be any outside force, right? Like air resistance, like some other person pushing on the object back, right? It's just it doesn't. It says only applies when there's friction. That's an
Oh yeah,
absolute.
friction is just one type of force that can
Yeah,
change kinetic energy. Oh
friction is
yeah.
just one type of force.
Mhm. Yeah. If two people do the same work, the one who finishes faster used more power. This one is true because remember, power is just work or change in energy over time. So if you do it in less time, which means you finish faster, you're dividing by a smaller number, so power will be greater. And chemical and thermal energy are types of mechanical energy. This is false. Mechanical energy is, remember, based on your position or like your ability, or like your ability to do work based off your position or your like physical properties, like your speed, what you're going at. That's what mechanical energy is. It's pretty simple. I'm gonna clear these drawings. Um, okay. Which of the following affects an object's kinetic energy the most? Mass, velocity, height, or gravity? Um,
Lucas, I'm gonna go in a breakout room with someone real quick. I think I'll be
okay,
back in
okay.
5.
Yeah. So this one is, if we remember kinetic energy, the formula is 1/2 mv squared. And the term that is squared is velocity. So velocity has the most impact on it. Because remember, like if you change it like a little bit, it'll be squared, like the discrepancy. So velocity is the greatest impact. Height isn't taken to it, and gravity isn't into it either. Which of the following is a
Lucas.
conserv? Hmm?
Never mind, never mind.
Oh,
I'm
which
trying
of
to
the
figure out
following is
how
a
this.
oh, okay. Which of the following is a conservative force? Remember, conservative forces don't take energy out of the system. So friction, that takes energy out of the system. It can't be this one. Air resistance takes energy out because remember, it's like turning kinetic energy into like friction or like sound. No, turning kinetic energy into like heat energy, which is taking energy out of the system. Applied forces are never conservative forces. You just kind of have to like know that. So it's gravity. The unit of power is this one is watts. You should have this memorized if you're going to be taking like a physics course or something. Super helpful to know. In the absence of friction, a falling object total mechanical energy uh increases, I think. Wait, I don't really get this question.
Hmm?
No, it stays the same. I think this should say like air resistance or something. Because anyway,
Lucas, do you know how to enter a breakout room?
no. Wait, give me 1 second. Okay, wait, yeah. So total mechanical energy is kinetic energy plus potential energy. I'm pretty sure, right?
Oh, what? Sorry.
Yeah, so total mechanical energy is kinetic energy plus potential energy. So if there's no air resistance or friction slowing down kinetic energy, as potential energy decreases, so as it's falling, kinetic energy is increasing. So like it balances out because both these are conservative forces. So this remains the same. Let me clear these. Okay, activity number 4, solving using formulas. A soccer ball has kinetic energy of 120 joules and a mass of 0.6 kilograms. What is the speed of the soccer ball? Um, okay, yeah. I'll just do this question for you guys. You guys can watch. Kinetic energy is equal to 1/2 mv squared here. And we know mass is given to us here with 0.6 kilograms. Oh, and they actually give us kinetic energy here, which is equal to 120 joules. So we know this is 3 variables. We know 2 of them. It's asking us for speed, which is this velocity here. And velocity is in this equation. So we can kind of just plug and chug. Oh, in space, there's supposed to be matter and antimatter. Why don't they cross out? I'm not too like knowledgeable on like astronomy, but I'm pretty sure if matter touches antimatter, they like explode or something. And I don't think antimatter is like super common in space, is it? Is antimatter- they are equal? Um, let me search it up. Okay. So I searched it up and it says physics rules say the Big Bang should have made equal amounts of antimatter and matter, but in like our observable universe, we mostly only see like real matter. Like we don't know where all the antimatter went, and that's like one of the puzzles in science. But yeah, if antimatter touches matter, they explode. It's like a big thing. Anyway, back to the question. So 1/2 times 0.6 is equal to v squared. Okay. So yeah, what is this potential energy at the top before it falls? I mean, half the space. Um, why did the computer say recording stopped? When Gotham left, it must have stopped the recording, but I started again, so it should be fine now. Um, a 1.5 kilogram ball is dropped from a height of 10 meters. Potential energy is equal to mass times gravity times height. We know mass is 1.5 given us still in the question. Times, we can assume gravitational acceleration is 10 meters per second squared to make it easy. Height is 10 meters here, so this turns out to uh 150 joules of potential energy. This is correct, right? Yeah. Okay. What is its kinetic energy just before hitting the ground? Oh, this one is kind of hard. Actually, wait, no, it's not. It's just equal to the potential energy, right? It's got 150 joules of kinetic energy right before it hits the ground because all that potential energy at the top just turns all into kinetic energy. At the very, right before it hits the bottom, it's got zero potential energy, which means it has to have like all kinetic energy. So all the potential energy turned into kinetic energy. So it's 150 joules. Is it 1500 joules? No, it's 150. What is its speed right before the impact? So we know 150 is equal to the kinetic energy. It's equal to 1/2 m, which is mass, which is 1.5 kilograms, right? It stayed the same, times v squared. This is 1/2 mv squared because I put in mass. And now we just have like a similar thing. We're just solving for v. So it's 300 is equal to 1.5 v squared. This is equal to 300 divided by 1.5. 200 is equal to v squared. V is equal to 20 again. Hey, that's kind of convenient. So 20 meters per second is velocity. Are there any questions? You guys get that? Um, what happens when fire starts in outer space? Fire needs oxygen to like stay a fire, and there's no oxygen in space, so you can't start a fire in space if there's no oxygen there. Uh, so it'll like if it's like on a spaceship, it'll burn until it uses up all the oxygen, then it'll just stop because there's no oxygen left. Okay, I'm gonna move on from this. Solving using formulas. Um, this is kind of like how many are there? I'll just do the last page of these. So activity 6, solving using formulas. Lena is building a homemade catapult using a heavy-duty spring. She attaches a spring with it. Wait, have you guys learned like spring forces yet? I wasn't here the last couple times. You guys know like spring potential energy and what those are? Yes. Okay. Um, you guys know like spring constant and everything? Okay, yeah, that's good. So I guess I'll start teaching this. Where's the object? So Lena, uh, like in the spaceship with people inside, will they die or burn up in space? Okay, so the fire is gonna be eating the oxygen on like the spaceship. So that means there's not like it's gonna use up all the oxygen. So that means the people will just suffocate to death if they don't burn to death. Lena is building a homemade catapult using a heavy-duty spring. She attaches a spring with a spring constant of 400 Newton meters, Newton per meter, to the launching arm. Before launching, she pulls the arm back 0.3 meters to store energy in the spring. She places a 0.2 kilogram rubber ball in the catapult and releases it. How much force, okay, A is how much force does the spring apply when stretched 0.3 meters? So we know spring force is equal to negative kx. K is a spring constant here, which is given to us. So spring force here, wow, so violent. Oh, I didn't mean it to be violent. It's equal to negative 400. Because remember, this is K here. It's given to us. Spring constant here times x, which is displacement, which is 0.3 meters here, right? So this is just like a plug and chug question, I guess. So negative 400 times 0.3, that's just, oh wait. Okay, this displacement is technically negative too, because you're pushing it back 0.3. So this cancels out, so it's just equal to 120 here. 120 newtons of force. And how much potential energy is stored in the spring before release? Uh, spring, do you guys know what the formula for spring potential energy is? 1/2 spring constant times displacement squared, which is like kind of similar to kinetic energy, but it's different. And like we can just plug and chug again. So 1/2 times 400 times 0.3. Wait, let's focus in chat, guys. 0.3 squared You can just use your calculator to solve this. It'd be 200 times 0.3 times 0.3 is equal to 18 joules of potential energy stored inside. Nice. Does everyone understand what happened? Okay, nice. Wrap up. Is this, let me see how much more we have. Great. I'll also go through this. So say what we covered is kinetic energy and potential energy. Wait, how much of this stuff did you guys do last time? I don't know. Um, we did like mechanical versus non. We did like the back half of this. Did you guys do like Hooke's law and like work energy theorem last time? Yeah, I think you guys did. Uh, I don't know if
We
we
did
should
all
do.
of that in the combining of two classes.
Oh, I see. Okay, I don't know how far I got them wants me to go. I think we're gonna do a book it actually. Let me go ask him. I wasn't there yesterday. Last class was where I'll be right back.
What is going on?
Okay, guys, I'm back.
Hello!
Uh, hi. We're gonna do centripetal force and then we're gonna do a book it. So this shouldn't take too long though. So we're like almost there. Okay, centripetal force. Does anyone have like any idea what centripetal force is? You guys think of like an example where you felt centripetal force or something? Well, like I guess if you were like swinging something like on a rope, have you guys ever done that before? Like you have like a string or something and you're swinging it around. The force that you feel like tugging on like the outside. Actually, no, that's like a fraudulent force. But anyway, centripetal force is like what keeps the object going in like a circle. It's kind of hard to explain. So yeah, centripetal force is the net force that keeps an object moving in a circular path. It always acts towards the center of the circle. So like when you're flinging like a weight around on a rope, centripetal force would be pulling it towards like your hand where you're swinging it from. Um, Without centripetal force, the object would move in a straight line due to inertia. It's not a new type of force. It's usually provided by tension, gravity, friction, or normal force. It's not like a its own force. It's just we just call it centripetal force, but it's just whatever force is pushing an object towards the center of the thing. So in this case, like if you're swinging something on a rope, it would be the rope tension that's providing centripetal force. That's kind of hard to explain. Here, centripetal force is mv squared over r. That's yeah. So m is mass, velocity is speed, and r is radius of the circular path. Um, what else to explain here? Yeah, the formula, centripetal force itself is given in the Newton's unit. Tension and centripetal force, hard question. Um, oh, this is kind of a hard question. Is there any slides after this? No, I think centripetal force. Okay, I guess I'll just like start walking through this then. I, I, I'll just walk through it because I don't think this. I think it's too hard for you guys to do on your own. Unless you guys want to do it on your own. Do you guys want to do it on your own? No. Okay. Let's walk through it then. So a ball of mass M. Oh, Gotham, do you want us to do this question?
Oh, um, probably not today.
Yeah.
I always do the
Okay.
hard question like a class after, because
Okay, okay.
yeah.
Should we just cut to the
Are you
booklet
guys
then?
done? Yeah, yeah, yeah.
Yeah, I finished everything else.
So, we'll do booklet for the last 10 minutes of class, but this booklet's gonna be on kinematics. This is gonna be on like the first two sessions we did of class, which is, do you want me to send you the booklet since you're already sharing screen?
Okay, okay.
Um, Here, I DM'd it. You don't want to booklet? I think it would be great if you guys did the booklet because booklets, this is gonna be a review for kinematics. And I know there was a lot of you guys that weren't there for the kinematics unit. And kinematic because kinematics is pretty important. And I don't want people, and we technically have 10 minutes left of class. So is it working for you, Lucas, the booklet?
Yeah, I'm trying to open it up. Okay, let me see
Okay.
what screen.
But I think you guys have, oh, you guys are doing fishing frenzy. Oh, did I open up to fishing frenzy?
Yeah, it was open as sufficient crunchy. We can do it for like 8 minutes.
8 minutes, yeah. Oh, 30. Okay, yeah.
Okay. Okay.
Penalty for incorrect, three random. Yeah. And then, yeah, that's good.
That's kind of loud.
No one can hear it except for you, I think.
Oh,
Yeah.
yeah, join on Bucket with this code.
Send link in chat. Oh,
Oh,
okay, you are. Right. You DM'd it to me.
jeez.
Did you send the link in the chat?
Yeah, it's
Yeah,
in the
we
chat.
are. Yeah, there we go. I sent it.
Wow, 18 participants. That's a lot of people.
Yeah. We're expecting 15 in the bucket.
Missing 5 people.
5 people. Four, three. And then there's late joining. Yeah. Um, please join. Three more
Yeah,
people.
it'll be fun.
Yeah, trust. And this is a good review for kinematics. This is, oh, yay. That's good. Yeah.
Someone named
It's a
themselves Bob.
kinematic.
That's
It's
funny.
pretty easily. It's pretty easy as well. You can, I think there's late joining, right, Lucas? So you
Yeah,
can
I'll
just
start
start.
now.
Please join if you were the one person who didn't. Please, please. And then give us feedback if this book gets too hard or is it if it's too easy or whatever. How did Ethan already get a 338-pound fish?
That's
That's
kind of crazy.
crazy. Oh my God. Is Ethan hacking, guys? Do you guys have those in the school still? I remember in middle school there would be people who just coded
Well,
to like hack Bookit. Was that you, Lucas? I feel like you would do
whoa.
that.
I did do that sometimes. No, but like I wouldn't do them like most of the time. Like some of the hacks, like they let you like unlock every single blockade. So I would use like the
Oh,
super
you
rare
use those.
ones.
Those are tough.
Hmm. Hmm.
Also, I know we gave the homework late, but um, two people turned it in.
Congrats to
Like,
those two people.
huh?
Congrats to those two people. You guys are good people.
If you guys didn't turn it in, like, that's okay because it was on us for giving it late. But also, like, just make sure you're like at least doing some practice. It doesn't have to be the homework we give, but try to do some practice just because it'll help with the repetition, right? And if you ever have questions on like any of the problems, like practice problems you're doing, just send us a message in Google Chats. We would be more than happy to help. But the homework we give you guys is like pretty easy and it'll take like 10, 15 minutes tops. So I
We'd
don't
really like it if you
like,
did it.
yeah, because it like tells us that you guys are practicing.
Well, Michelle is cooking you guys. I can't lie.
Ooh, 10K. Yeesh. Ethan, lock in. You were at first place before. Oh, oh, Ethan took it back. Ooh, what, 3 minutes? Two minutes. Lock in. Ooh, Neil's in first place.
We're Neil locked in, bro. What even catch?
Probably got a Megalodon, no?
Yeah,
No, wait. Sheesh. Do you think we can post this book in Google Classroom as well? Just for them to.
maybe.
Oh yeah, it's fine if you guys are also like struggling in the book it because I know you some people didn't cover some people didn't cover the like cover the kinematic classes. And then I know a lot of some of these questions are also a lot harder than the others. So it's totally fine if you guys are not doing so well. Each top seven of Hall hit over 100K. Right, what? Do you want to end it right now, Lucas?
Yeah, sure.
Just Michelle in third place, Ethan in
Congrats to the top
second,
three.
and
Good
Neil
job,
in
Neil.
first. Wow,
Very
top
nice,
three
Neil.
locked in. I think
Okay,
overall
this.
everyone had a good amount of pounds though. So
Mm-hmm.
good amount of
All
fish
right, good
caught.
job, guys.
I I think class is done. You guys are feel
70%
free to go.
accuracy. See you
I'll take
guys.
70% accurate. That's
This is
that's
pretty
that's
good.
pretty good. That's a D plus. Um, yeah,
You guys are free to go now.
yeah. You guys are free to
That was
go.
low-key easy. Good job, Neil.
She's just flexing on everyone. All right. Yeah, if you guys have any questions, feel free to stay. But Lucas and I will be on. Lucas, stay on call for like 5 minutes
Yeah.
after.
Question repeated, so it was easy. Oh, I see. Bye, guys. Yep.
Bye.
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 Dennis, do you have any, Thomas, do you have any questions?
Oh, are you gonna ask about your brother? Yeah, we low-key don't know where your brother is, Manish.